Okay, let's check, and we're recording. Okay, so in order to do this optimization for the final project, we're going to apply one of the optimization algorithms that's built into MATLAB. It's called fgoal_attain, and I've put these two files up on Isidore, and basically what your job is for task 5 is to use these two files and kind of fill in the blanks. So I've provided you with all of the basic code. I've left, I don't know, I think 5 or so lines unfinished, and you have to basically fill those in based on what you know about the problem. So what fgoal_attain does is it's an optimization that helps us to meet some sort of goal that we decide that we want to achieve. And so it helps us come up with the best solution to reach that goal. So we know that in the final project, we want to optimize a certain variable, a certain parameter about our roller coaster. And we want to achieve a certain goal about the roller coaster as well. And so we can use that information to kind of populate and fill in these blanks here in this document. So what your job is to do is to fill in a couple of these blanks, and then the rest of the code you kind of just leave as is and don't touch and don't change. So the first thing that you'll see up here at the top of the file is what's called options. That's settings for the actual optimization function in MATLAB. I've set those up in the way that I think that they should be set up, so I would very strongly urge you not to touch those. If you do, the only thing I would suggest potentially changing is this maximum number of evaluations, but I would highly suggest just leaving it as is. The things that you will need to fill in here are these 4 values. So these should all these variables should be equal to one single number. And the first one, opt0, provides the optimization some sort of initial guess for the quantity that we're trying to optimize. And that could be, I would strongly suggest that you base that on some information you might have gotten from task 4 about your roller coaster. And I'll kind of leave that up for your interpretation. You also have to define the goal, so you have to have some way in an optimization to quantify what your goal is. So that's going to also be a number. When we do goal-based optimization, sometimes we can have more than one goal. So I might want to, if I'm designing my cell phone, I might want to minimize material cost and minimize the weight. When I do that optimization at the same time, I've got to decide which one of those goals is more important. Is it more important that I minimize the weight, or is it more important that I minimize the cost? If I only have one goal, which we do in this problem for the roller coaster, I don't need to worry about weighting because I only have one goal to achieve. And so in that case, MATLAB suggests that you set the weight equal to the goal. So that's what I would suggest that you do in this problem. The other thing that you probably want to specify in this file is this variable LB, which is the lower bound on the quantity you're trying to optimize. So you need to think about what's the thing that we're trying to optimize, and what's the lowest reasonable or feasible value for that parameter that you would potentially accept. So you need to decide what's the lower bound, where do we want to cut that off, and say I'm not going to accept some value below that. So those are the 4 things you have to specify in this file. And then if we scroll down at the bottom, I've got a lot of comments in there to kind of explain what's happening. And this is where we're actually using the fgoal_attain function. And so the fgoal_attain function actually runs the optimization, and I'll show you in a minute what that kind of looks like. And it uses what's called a goal function. So when the optimization is running, it's making guesses for the parameter that we're trying to optimize. So it's guessing this number, and it's guessing that number, and it's guessing a bunch of numbers, and it's going to guess maybe 50 or 100 different guesses for that parameter we're trying to optimize. And it's got to have a way to evaluate which one has achieved our goal and which ones are really far away from achieving our goal. And that's what happens in that goal function. And so we're going to write, I've given you, again, kind of a skeleton for what that function looks like, and we'll talk about that in a minute. And then all the rest of the inputs into the fgoal_attain function, a lot of them are things that we specified up at the top. And then there are what's called kind of an empty matrix in MATLAB, which basically tells MATLAB I don't care about that parameter, so I don't want to set it to anything. So the output out of the optimizations, we get two different things. We get opt, which is the final value of the parameter that we're trying to optimize. So it's going to be basically our answer to the problem. And that's what's going to be, the number in opt is going to be the answer basically to our problem. So what's the optimal value of the thing we're trying to optimize? And then we also get our final value of our goal. If the optimization did a good job, then goal final should be equal to the goal that we set up at the top of the optimization, the goal we were trying to achieve. If that's not the case, then maybe we did something wrong when we were setting up the optimization, or we might have given the optimization a bad initial guess. So we had to specify that initial guess up here. That was what was in opt 0. If we don't kind of point the optimization sometimes in the right direction, it can get lost, and it cannot find a good solution. So you've got to evaluate what you get, the results that you get out of the optimization. Did it achieve your goal, and kind of do the results make sense? If not, then I would suggest changing that opt 0 value to something different and seeing what happens when you get that final answer. Did it change it? Does it still be, is it still consistent? Does it make sense? So that's what this file has in it. Any questions about that so far? Yes, ma'am.
So for the optimization part of the project, do you want us to put this in the same script as the first part, or do you want it to be completely?
This will be a separate script that will kind of, so now this is what you will run to kind of run the project. And then it will in turn run all the other parts for you, basically. So this is the thing that you will run for part 5 and part 6, this script here. So, so we said we have to run this goal function, or we have to write this goal function. So again, I provided kind of the framework, and you just have to fill in a lot of the blanks. So what's happening when we get to this function? So the optimization is making a bunch of different guesses for that opt parameter, the parameter that we're trying to optimize. And every time it makes a guess, it's got to decide, is that a good guess or is that a bad guess? So it comes over here into this goal function, and it tries to evaluate if it's a good guess or it's a bad guess. So as an input to this function, we get the current guess, the opt value. So it says, okay, I'm going to guess that that parameter has a value of 200. And we get that number as an input into this function. And then we've got to do something with it. So in the roller coaster problem, we're trying to optimize some parameter about our roller coaster, and we want to see how that affects how the roller coaster moves down the track. So we're going to get that value, we're going to get that number as an input to this function, and then based on that information, I want to send my roller coaster down the track. And if I send my roller coaster down the track, I'm going to have to integrate my equations of motion, because I got to figure out the position of my roller coaster over the whole track. So I've got to figure out what's the influence of that parameter on how my roller coaster is moving down the track. So I'm going to need to use my ODE 4.5 function to do that. So right here in this middle chunk here, this code should be almost identical to what you have in your script that you wrote for task 4. So you have to fill in the time span, you've got to fill in the initial position, initial velocity, and then the only thing that you should have to change in here is instead of having just this generic task 3 function, you got to fill in the name of your function that you wrote for task 3 there. So that's what you would fill in there. And then actually in the task 3 function, so whatever you wrote for that, you're going to have to add in this extra parameter. So as the input into the task 3 function, we had 2 inputs. We had t and we had states. We're going to add in a third input, opt, which is now going to replace that value of the parameter. So for this problem, we're optimizing the engine thrust. I told you to set it to 1500 in task 4. Now we're not going to set it to 1500 anymore. We're going to set it equal to this input parameter, opt. So you're going to have to add that third input to your task 3 function, and then use the opt variable inside the task 3 function instead of setting the engine thrust equal to 1500. And then, so if we do that, we're going to send our roller coaster down the track, and we're going to get back the position, and we're going to get back the velocity of our roller coaster over time. That's what we get out of the ODE 4.5 function into our solution. And based on that information, we should be able to verify and kind of tell MATLAB if that guess for the optimal engine thrust was a good guess or a bad guess. And where we do that, we have to quantify that by one single scalar value. I'll repeat that again. Goal down here at the bottom of this function should be one single scalar value. If it's a vector, you're going to be in trouble. If it's anything but that, you're going to be in trouble. So it should be a one single scalar value. It also should depend on your results from your ODE45 function. So it should not be one number that you type down there at the bottom. So that number should not be 10 or 1,000 or whatever you think it should be. It should be, I'm going to tell you, some part of this solution matrix. It's going to be a number that comes out of that solution matrix. You just have to decide what number that is. So that's my strong hint for that. Any general questions about this? There's more explanation in the comments. There's more explanation in that handout I gave you at the beginning of class last time. And now I'm going to just quickly show you what this looks like when it's running so you can kind see. I can explain what it means. So where is my, oh, here it is. Okay, so this is what's going to happen when you actually get your optimization running. So what is it doing? It's making a bunch of guesses for the parameter that we're trying to optimize or the engine thrust. And so as it's doing that, we're going to get more and more dots on this plot here. So what's actually happening? So on the x-axis here, we have the number of guesses that it's made for that value. So we have roughly 20 values on the x-axis, so it made 20 different guesses for the engine thrust. Oh, still going. I thought it might have stopped. And what we can see on the y-axis is the current value based on that guess of the goal. So our goal is to achieve some sort of result from our optimization, and what we see on the y-axis is how well we're achieving that goal. So with our initial guess, so our very first iteration over here on the far left, our initial guess was some value for the engine thrust, and we can see that the resulting goal was pretty high. So our resulting goal was like 1,027 meters. So the distance down the track was 1,027 meters. So that was higher, maybe, than what we wanted to achieve. So the optimization said, okay, I'm going to try another guess down here. That was probably too low, and you can see that it kind of iterates back and forth, back and forth, back and forth, until it finally converges on some value over here, and we're still kind of running. But you can see that it's kind of converged on some value that may possibly represent our solution. So when we are done with the optimization, it's going to stop, and over in the command window, you'll see that it's printed out all of this stuff. Honestly, we don't really care what that stuff is saying at this point, and we don't really care about what this message is. So you might get this message, you might get a different message that comes out of it. At this point, we're going to kind of not really care what those messages say. I'd be happy to explain what they mean to different people, but for the general knowledge, we don't really need to know what they say at this point. What we need to do is we need to evaluate the results that come out of this optimization. So the parameter opt and the parameter final goal, make sure that they make sense, and if we're happy with those, then we can say that our optimization has succeeded and done a good job. So that's what's happening with the optimization. So when you get it to run, hopefully you will get a plot. Yours is not going to look like this. It's going to do something different. Everybody's is going to be different, and that's where you're going to get your kind of final solution to the problem. Yes, sir?
So, that number, that 998,
Yep.
is that your goal final?
That's the final goal, yep. So it's going to be here at the top. It's also going to be in a variable in your workspace. So you've got it in two places.
Okay, so since I'm assuming you didn't get, have that as your initial, like, guess.
Well, that's the goal. So your initial guess is related to the parameter that you're optimizing. So those are two different things. But
So you want to,
And actually, I'll say the last value that gets put up here at the top of that, this figure may or may not, it's going to be close to probably your final value, but it may or may not match up exactly. Because not always does the last guess end up being the best guess. But a lot of times it is. So, any other questions? All right, I will let you guys work for the rest of class today.